Have you ever felt ambushed by string windows? Find all anagrams in a string is a Pattern Mastery 100 essential that exposes whether you truly own sliding windows and frequency counts. Phong interviewers love it because a brute force check is too slow, but with the right window math, we get linear time and clean, confident code. Let's nail it with basics. Let's break this down. We're given strings S and P. We must return all start indices in S where the substring is an anagram of P. Only lowercase letters. The anagram condition means the character counts match. Now let's assess. Naively sorting each window is on middle.m log m, too slow. Instead, we maintain a fixed size sliding window of length len p over s and compare letter counts. 2 standard tactics. Keep 2 frequency arrays of size 26 and compare. Track a matches counter that says how many letters currently match p's count. We'll use arrays plus matches for O1 updates and ON time, O1 space. Here is the structure. Plan. Build need 26, from P. Sweep right over S, incrementing have C. Once window size exceeds len P, decrement the left char and move left ++. Maintain a match count. When have X equals need X, increment. When it stops equaling after update, decrement. If match equals 26, push left to results. Let's try to implement it using solution 1. Line highlighted, import java.util. We import Java utilities because we'll need lists and sorting tools. Think of this as grabbing a toolbox before we start building anything. Line highlighted, class solution. This begins our solution class, where all the logic for finding anagrams is stored. Line highlighted, public list integer find anagram string S string P. This method will return all starting indices in S where an anagram of P begins. Line highlighted, list integer res equals new array list. We make a list to store any valid starting positions we find. Line highlighted, int m equals p.length, n equals s.length. We store the lengths of p and s so we can compare windows efficiently. Line highlighted, if m greater than n, return res. If p is longer than s, it's impossible for an anagram of p to appear inside s. We immediately return an empty list. Prepare the sorted version of p. Line highlighted, char, p chars equals p.toChar array. We convert p into a character array so we can sort it. Line highlighted, arrays.sort p chars. We sort the characters of p. Sorting puts the letters into a predictable order. Line highlighted, string p sorted equals new string p chars. We turn the sorted characters back into a string. This gives us a signature that all anagrams of p must match. Pause. Time complexity note. Sorting p takes om log m. Time. Slide through S, checking each window of length m. Line highlighted, for int I equals 0, I less than equals n, m, I++. We loop across S from left to right, stopping wherever a substring of size m can still fit. Line highlighted, char, sub equals s dot substring, I plus m. To char array, for each position I, we grab the next m characters. This is our candidate substring. We convert it to a character array. Line highlighted, arrays.sort sub. We sort the substrings characters, just like we sorted p. If 2 strings are anagrams, their sorted versions will match exactly. Pause. Time complexity note. Sorting the substring takes om log m, and we do this for every position. Overall becomes on times m log m. Very expensive for large inputs. Line highlighted, if p sorted dot equals new string sub, we compare the sorted substring with the sorted version of p. If they're equal. Line highlighted, res.add I. That means we found an anagram starting at index I, so we add I to our results. Line highlighted, end of the if check. Line highlighted, end of the loop that scans all possible windows. Line highlighted, return res. We return the list of all starting indices where anagrams were discovered. Line highlighted, end of the method. Line highlighted, and this closes the entire class. Final wrap-up summary. And that's how this algorithm works. It first sorts the characters of P, then scans through S1 substring at a time, sorting each and comparing it to the sorted target. If they match, we mark that starting index. Efficient, simple, and elegant, although sorting each window repeatedly makes it slower than optimal sliding window solutions. Highlight input box, S equals key B bobuct, P equals ABC. Let's test our function with the string P B bobuct and the pattern ABC. We're looking for all starting positions where an anagram of ABC appears inside S. Explain logic briefly. The first 3 characters of S, kaba, contain exactly the same letters as ABC, just in a different order. So index 0 is a valid match. Later in the string, the substring block also matches the pattern, which starts at index 6. Highlight output box. Output, 0, 6. That's exactly what the program returns. 0, 6, matching the expected result. So the implementation works correctly. It finds every anagram of ABC by sliding a fixed-size window across the string and comparing character frequencies. Let's try to implement it using solution 1, but now narrating solution 2, the optimized sliding window plus frequency array method for finding anagrams. Line highlighted, import java.util. We import Java utilities so we can use lists and arrays. Line highlighted, class solution. We begin with the solution class, which contains our optimized anagram finder. Line highlighted, public list integer find anagrams string S, string P. This method returns all starting indices in S where an anagram of P appears. Basic setup. Line highlighted, list integer res equals new array list. We create a list to store every valid starting index we find. Line highlighted, int m equals p.length, n equals s.length. We store the lengths of p and s to simplify conditions later. Line highlighted, if m greater than n, return res. If p is longer than s, an anagram is impossible, so we immediately return an empty list. Pause. Frequency arrays for faster comparison. Line highlighted, int p_count equals new int 26. This array tracks how many times each character appears in P. Line highlighted, int window equals new int 26, and this array tracks character counts inside the current sliding window of string S. Count characters in P. Line highlighted, for char c p.toChar array. We iterate through all characters in P. Line highlighted, p_count c a++. We increment the position corresponding to the character. Subtracting a maps a to 0, b to 1, and so on. Build initial window of size m. Line highlighted, for int I equals 0, I less than m, I++. We fill the first window, the first m characters of S. Line highlighted, window s.char at I, a++. We count how many times each character appears in this initial window. Line highlighted, if arrays.equals window, p_count. We compare the window's character frequencies to those of P. If they match, the window is an anagram. Line highlighted, res.add 0. If so, we add the starting index 0. Pause. Time complexity note. Each comparison is O26, which is constant. So the entire sliding window runs in ON time, a huge improvement over sorting each substring. Slide the window across S. Line highlighted, for int I equals m, I less than n, I++. Now we slide the window one character at a time until we reach the end of S. Add the incoming character, line highlighted, window s.char at I, a++. We include the new character at the right edge of the window. Remove the outgoing character, line highlighted, window s.char at im, a-, and we remove the character that just moved out of the left side. Check for anagram match. Line highlighted, if arrays.equals window p_count. After updating counts, we check if this new window matches P's frequencies. Line highlighted, res.add I, m+1. If it does, we add the starting index of this window, I, m+1. Return results, line highlighted, return res. After sliding across all possible windows, we return all starting indices of valid anagrams. Line highlighted, close the method. Line highlighted, close the class. Final wrap-up summary. And that's how this algorithm works. It first counts the characters of P, then slides a fixed-size window across S, updating character counts in constant time, and comparing the window to the target frequency. Efficient, reliable, and elegant. Highlight input box, S equals key B bobuct. P equals ABC. Let's test our function with the string P B bobuct and the pattern ABC. We're looking for all starting positions where an anagram of ABC appears inside S. Explain logic briefly. The first three characters of S, kaba, contain exactly the same letters as ABC, just in a different order. So index 0 is a valid match. Later in the string, the substring block also matches the pattern, which starts at index 6. Highlight output box. Output, 0, 6. That's exactly what the program returns. 0, 6, matching the expected result. So the implementation works correctly. It finds every anagram of ABC by sliding a fixed-size window across the string and comparing character frequencies. Sliding windows can feel sneaky, until you see the pattern. Find all anagrams in a string turns chaotic substring checks into a calm, linear pass with tight frequency math. Let's do a recap. We're given S and P, and we need all start indices in S where a length vertical bar P vertical bar substring is an anagram of P. Conceptually, match character counts, not order. Sorting every window is too slow. The right idea is a fixed size sliding window plus frequency counts. Maintain counts as the window moves so each step is 01. A small matches tracker tells us when the window's counts align with P. Build the target frequency for P. Sweep a window of size vertical bar P vertical bar across S. Add the right char, and when the window exceeds size, remove the left char. After each update, adjust the matches counter. When all tracked letters match, record the window start. We executed that plan. Pre-computed counts, slid the window with constant time updates, and captured indices exactly when the counts aligned. The solution ran cleanly on LeetCode with no errors. LeetCode verification confirmed the approach. Indices were collected correctly and all test cases passed as expected. Bullseye emoji. The lesson: sliding windows shine when you trade rework for maintenance. Keep counts in sync as you move, and anagram detection becomes fast, simple, and reliable.